Hello and welcome to In Control, the first podcast on control theory. Here we discuss the science of feedback, decision-making, artificial intelligence, and much more. I'm your host, Alberto Padoan, live from our recording studio in Zurich. Quick thanks to our sponsors, the National Center of Competence in Research on Dependable Ubiquitous Automation and the International Federation of Automatic Control. Our guest today is again Naomi Ehrich Leonard. She's the Edwin S. Wilsey Professor and Chair of Mechanical and Aerospace Engineering at Princeton University. Welcome to the show, Naomi, again.
Thanks very much. It's great to be back.
So in the past episode, we covered the first part of your journey into research, but today we're digging into some of the applications that have been driven by animal studies that I find super fascinating, and I'm looking forward to exploring them together. I honestly don't know where to go from here, because there's so many interesting topics that we could talk about. Starlings, we could talk about chasing zebras in Kenya. Mm-hmm. We could talk about ants, foraging ants in the desert. I'll let you choose.
Okay.
And what was the most fascinating for you?
Well, I can't use the word most. They're all incredibly fascinating. I can talk about a couple of these things if you want.
Absolutely.
The work that we did with the Starlings was really exciting. And they were all different kinds of steps in my path. And that one was actually focused on linear dynamics. And I had met Andrea Cavagna and Irena Giardina, who were part of this project called Star Flag. And I think I met them in 2007 when I was on sabbatical in Italy. And I think I had just met them previously in Princeton, and then I went down to Rome, and they had collected with their team this incredible data set, which was the Starlings that fly over the train station in Rome, and they had spent several months with cameras on the roof of a building and being able to triangulate. It was the first time ever that we had seen what the volume of these flocks looked like, and collecting this data in 3D. It was incredible. And they spent a huge amount of time trying to actually do the processing of these images that they got to understand. You can imagine you have a flock of 1,200 birds from one frame to the next. It's very hard to even see. There's so much occlusion, and they look alike, and figuring out what was going on. And so they did all this beautiful work, and they wrote this beautiful paper. It had to do with what they call the topological metric, and they showed essentially using this argument from statistical mechanics, making use of an anisotropy, this idea of essentially looking at where a focal bird's first closest neighbor was located, second closest neighbor, third closest neighbor, and showing that it was more likely to be, say, the first few on the sides and then maybe above and below. But when they got up to 8 neighbors or more, it was isotropic. It didn't matter. It was uniformly distributed where the 8th neighbor was. And so they made this argument that the birds were only paying attention to up to 6 or 7 of their neighbors. It was really super elegant. And so I met them at this time, and they had explained to me that they thought that this number, that the whole story really had a lot to do with the robustness of the group, the ability of the group to form consensus about where they were going and move so smoothly and beautifully together. So I think at that time I'd gotten interested in noisy linear consensus and this idea of trying to understand the role of the network structure on the ability of a group to be robust. We know how to compute for a dynamic following linear consensus with additive white noise. We know that the group makes a random walk around consensus, and the consensus value can drift, but you can compute the steady state variance. Actually, you compute it using the Lyapunov equation. You get the covariance, you take the trace. And actually, you don't have to assume that the network is symmetric, so it doesn't have to be undirected. So if you've given a bunch of points in space and you're told that every bird is paying attention to its 6 or 7 closest neighbors, it's not going to give you an undirected graph, because you might be one of my 6 or 7 closest, but I might not be one of your 6 or 7 closest. But you can still do that. You might have a 1,200 by 1,200 dimensional matrix matrix equation that you have to solve. But my student at that time, George Young, was super smart, wrote some beautiful code that we could do this. So we study this with these scientists, which is absolutely fantastic to do this in collaboration, trying to really understand what we were doing and how to interpret the data and what it could mean. And of course, this notion of robustness is one that we care about in systems and control theory. But and for the birds, it may have been one of the things that there's probably many ways in which these birds are robust, but it was kind of interesting just to sort of essentially explore this idea, right? And so we took something like 400 frames, and the birds moved so fast that we could treat each one as kind of a steady state moment. And so for each frame, we then computed the network with a hypothesis that each bird was paying attention to. 1 closest neighbor, 2 closest neighbors, all the way up to 11. And then for each network, we could compute essentially a score, right? We ended up looking at the first at the inverse of the dispersion of the steady state variance. So I think it took something like 3 neighbors for it to become connected. And then you started to see this thing rising. Of course, it rose with every additional neighbor, but what we saw was that it rose steeply until you got to 6 or 7. So then when we divide by the number of neighbors, we're looking at the per neighbor contribution to reducing that variance about consensus. It's optimal at 6 to 7.
6 or 7.
Yeah.
I need to look at 6 or 7 of my neighbors if I want to be basically gravitating around consensus.
Yeah.
And therefore save myself also, I guess, as a starling.
Yeah. But it's connected to the way they have organized themselves spatially. So we also explored how was 6 or 7 related to being sort of a few birds thick. They're not these big spheres. They don't move in a spherical formation. They move more like a fluffy pancake, And so which comes first? Is it the way they move, and then they pay attention to the number of neighbors according to that? The causality, I don't know, but these relationships was super interesting to study. So that was one study that influenced me, because thinking about how network structure affects property like robustness is very important for us as we're thinking about how to design network structures in the technological world. And another really important work, and in fact, it's becoming even more important to the things I'm thinking about today, is the work that my former student Renato Pagliara and I did with the biologist Deborah Gordon. So she's a biologist at Stanford who studies ants, and just incredible. And she has been censusing these ants in the desert of Arizona for more than 30 years. And so she's knows so much. And she had, in fact, met John Doyle and learned about our field and learned about feedback. And then I subsequently had met her at a workshop that I had organized with Mahadevan at Harvard at the Radcliffe Institute, where we brought together physicists and biologists and computer scientists and control theorists to talk about collective behavior.
Okay.
And so Deborah and I chatted there, and she told me about her question. And she had already been working with some neuroscientists to think about this question, but it had to do with these ants that don't leave pheromone trails. So they forage by just going out on prepared original tracks, and then they wander until they find a seed, and then they come back. So they could wander pretty far. They're called harvester ants. And so they all are in the hive, and some of them come up and make themselves available to go and forage. And she knows very well how they make these decisions. Essentially, an available forager is waiting, and as foragers come back with their seeds, they greet the available foragers by touching antenna. And so the forager who's waiting, potential forager who's waiting, at least knows that they've been outside, because it would feel different if they just bumped into a neighbor and greeted one another. They would know that wasn't an incoming forager. And so she knows very well that it's the rate at which they're getting greeted by incoming foragers. When that rate is above some kind of threshold, they'll go out. If it's below that threshold, they won't, right? And this is really important. And the question she was asking had to do with resilience to the changing conditions in the desert. So when it's hot and dry, the ants should not be going out because they have enough hoarded seeds to survive, and they could expend more water than they would get from those seeds. But when it's humid and cool, they should definitely go out. And she understood that across the colonies, there were different strategies. So some were maybe more exuberant and would go out, and then when they would realize, or somehow realize through this communication that it was too hot to be out there, it would take a while to get back in, whereas the ones who are more careful and more circumspect and go out more gradually, if they needed to come back in, they could, or they could go out. And eventually these always equilibrate. When they stay out, they equilibrate, so the incoming rate is equal to the outgoing rate. But sort of that transient, that's super interesting. And so she asked us if we could come up with an understanding of the mechanism that was parameterizable so that she could see what they were doing in response to, or what hypotheses she could try to rule out with experiments to understand what might be going on, where they were easy to interpret or understand dials or parameters that would allow her to understand how to distinguish colonies. Renato and Deborah, when they went out, they collected these data of the rates of outgoing and incoming. And
you have to literally count the ants that come
literally
out.
counting the ants, as they're crossing. I mean, you could do it with a camera and then do it.
But it makes sense. You're basically trying to identify the system, quote unquote.
Exactly.
So you're trying to identify a certain number of parameters that allow you to predict the behavior of a certain hive.
Exactly.
Yeah.
She had been working with people looking at the leaky integrator, so if like filtering and then thresholding kind of models from neuroscience. What we wanted was a self-contained dynamical system. So we used a Fitzhugh-Nagumo oscillator, so a nonlinear oscillator that would allow us to understand tunable parameters. And we basically had a parameter that tuned the frequency of this oscillator. And you could think about every cycle, a spike in the oscillator as an ant going out. That's not hard to understand. And it fits in Nagumo how you might tune that. But what we did was hypothesize that the ants, when they are first getting ready in the morning, it's the same temperature and humidity inside the nest, so they don't necessarily know what it's like outside. And it's only after they've been exposed to the outside that they can learn. So we basically had two Fitzhugh-Nagumo oscillators running, one with the uninformed parameter, which might be the default frequency, were things to be based like their default behavior. And then there would be the informed one, which could make the frequency go up if they experienced it, that it was a beautiful day, and it could make it go down if they experienced it as a not so great day. And so
the informed part is basically the sensing. Responsible for the sensing.
It's the sensing, but it's this gradual process. So you can think of the ants in the uninformed category, and then they're slowly, as they go out, then they join the informed category. We didn't want to have to just make up some rule for how this parameter would change. We wanted to understand it through how the ants were moving. And so there was a little bit more to the story to try to understand how this worked, and also how to prove something about the trends, that we could see the qualitative behavior, and then we could explore how that could explain the range of behaviors. That was sort of the idea. Could we get a system that could explain the range of behaviors, like the behaviors where they went out and they equilibrate at a really high rate, when they come out and they equilibrate at a lower rate, when they come out and they come right back in.
In the paper, which by the way is a regulation of harvester ant foraging as a closed-loop excitable system, you have this nice picture where you have these basically 4 quadrants that classify the different behaviors of the ants, and it seems that the model you propose actually replicates fairly well the experimental results that you have by counting ants in the desert. Just a small clarification again for our audience. So what is a Fitzhugh-Nagumo model? Fitzhugh-Nagumo model is just an oscillator model, 2 variables for replicating neuronal behavior. It's a basic neuronal model. There are others, of course, out there, but it's a simple example of an excitable system, so that it's very sensitive to thresholds, potentially.
Exactly. It allows you to understand these implicit thresholds that emerge. And that paper led us to think about, we had this observation that the process that they were going through could be compared to an infectious process. So this idea that this tendency to want to go out and forage, you could think of as like the passing of an infection. And so this idea to try to understand the ability of a group with very limited communication, really just through contact, how that could lead to this different kinds of behaviors, as you explain, the quadrant of behaviors. And so we explored these ideas in one of these compartmental epidemic models.
Yeah, I guess you're implicitly referring to SIR models as they are known in our literature or in the dynamical systems literature. I forget the acronyms. I think it's susceptible, infectious, and resilient.
Recovered. Yeah.
Recovered. Those are also very popular, I guess, also recently due to, unfortunately, the COVID epidemic that we faced. They've been used to model also and explain how certain diseases spread. One thing that I want to mention is that there is a fantastic paper that I recommend the audience to read, 2014. It's in the annual reviews in control that you wrote called Multi-Agent System Dynamics, Bifurcation and Behavior of Animal Groups, because it gives a fantastic overview of your research up to that point, of course, up to 2014. And the work that we mentioned just now on ants dates back to 2018. So there is still a lot of research going on. Okay, so we've talked about harvesting for foraging ants, decision-making for bees, pattern formation for starlings, but it seems like all of these themes coalesced into one organizing theme, which is that of decision-making both in human, but also in animal, and even cyber-physical systems. This seems to be something that you're looking at most recently, and we were mentioning that offline, that you have an upcoming publication on the subject.
Yes, we have an upcoming publication in the annual review of control robotics and autonomous systems called Fast and Flexible Multi-Agent Decision Making, which reviews this whole area with a particular focus on the need for systems, whether natural or designed, to be fast and flexible when they're going to operate in environments that are complex, that have uncertainty, that have variability, that have things that change dynamically. And how does that work?
And so how do we analyze and design such systems through, say, bifurcations theory, singularity theory, and all these concepts?
So our starting point that built on body of work, understanding decision-making in the natural world, also understanding other kinds of network systems in particular in neuroscience, how networks of neurons exhibit the kind of flexibility and fast dynamic that we are interested in more generally, led to thinking about, well, our starting point was to think about decision-making as a nonlinear dynamical process that changes continuously in time, knowing that what we observe as sometimes switch-like behavior can actually occur through bifurcations. So we don't actually need to think about a system as having a hybrid element or a logical element in order to get switch-like behavior. Mm-hmm. In the natural world, these systems are evolving continuously over time, so it kind of made sense, but also in the context of design, it still makes sense because we have tools to study nonlinear dynamical processes. So that was our starting point. And so the step was to really understand how to abstract out these principles and understand how to develop a mathematical framework that would be an abstraction of what we understood to be the mechanism underlying this kind of remarkable collective intelligence. And the focus was on decision-making, thinking about how, in particular, decisions or opinions form from very little input. So small inputs or small initial conditions, how opinions can form. Essentially, how does indecision, how does neutral get broken, and how do we see the formation of strong opinions coming quickly and sensitively when they should. So when I say we, this is work in collaboration with Alessio Franchi, who's at University of Liège, and Anastasia Bizyaeva, who's my former PhD student, who's now at the University of Washington. But plus collaborators, Vaibhav Srivastava and Beck Gray, former student. I've built this along the way with a whole bunch of collaborators, and as well as some mathematicians who have helped us understand geometric space of decision making and understanding ground.
Among which the man himself, Golubitsky,
and more recently Ian Stewart, trying to understand the underlying theory of decision making on networks. Mm-hmm. So the first paper we wrote was an attempt to take the decision making of honeybees, which was studied using a mean field model and transforming it into an agent-based model on a network. So this interest in understanding the role of the network structure. What is it about the network, and how do we quantitatively translate between behavior and who's paying attention to whom or who's observing whom? Yeah. It grew into a second paper which generalized the first paper. The first paper appeared in 2018 in IEEE Transactions on Automatic Control. So I think it was called Honeybee-Inspired Opinion Dynamics, or Nonlinear Opinion Dynamics. And the second paper was in 2023. It just appeared in print. It's called Nonlinear Opinion Dynamics with Tunable Sensitivity. But the idea was to use this principle of a continuously evolving dynamic on the evolution of an individual's opinion. So each individual agent in the network has an opinion that's a real valued opinion about every possible option. The more positive it is, the more in favor of that option, the more negative it is. So it's less in favor. And when it's zero, it's neutral about that option. So it might have a whole vector of these opinions. And these evolve in a way that's actually modestly nonlinear, but makes all the difference. So there's a term that's just negative feedback that regulates you to neutral in case nothing else is happening. There can be an additive input, but then there is the all-important positive feedback you can think of as the weighted sum of all the opinions that you can observe. So through a network, you can think of as a communication network or as a sensing network. We also imagine that there may be what we call a belief system network, so that there can be weights that inform, if you're, say, for one option, how that affects your opinion about another option, because they may be closely connected. And so this weighted sum of opinions, we also attach to it a gain, and actually that gain turns out to be a variable, and we call it attention. Going back to the honeybees, this is kind of like the stop signaling rate. It's related to under what conditions are you really paying attention to these observations that you have. If it's important, if there's some reason that you should be paying attention because you're about to collide with somebody and you have to choose whether to go left or right, your attention will grow. Or the election's coming and somebody just sent you some articles to take a look at, then your attention grows and you become engaged in that process. So there are dynamics based on a feedback mechanism. So you're looking at the opinion states of others. And if no one's forming opinions, no one's engaged, then you don't become engaged, but you might become engaged either because you see somebody else engaged or because through that little bit of input that you've gotten, your own opinion starts to grow, even if it's linear. Yeah. Then it can set off a growth in your attention. You pay attention to things. But that attention-weighted sum of opinions gets operated on by a nonlinearity. So this is how the system becomes nonlinear, and we use a saturation function. So it's dealing with the paradox that if somebody is screaming really loud, maybe you cut them off. So if it's a smaller, modest kind of sum of observations that you're getting, you just treat it as it is. But if it grows too positive, too in favor, or if it grows too negative, you just essentially saturate it. But this makes all the difference. And I should say that this isn't really an ad hoc story. We have developed a model-independent story, which is a geometric look at the space of opinion formation, the space of opinions. One direction is a consensus direction where everybody is perfectly in agreement, and then the rest of the space has to do with dissensus or disagreement directions. But what we understand in this setting is how to consider the case in some sense, the most symmetric. The most symmetric is when, that you can't distinguish between options and you can't distinguish between agents. Everything is so symmetric and homogeneous. The number of things that can happen is maximal, right? Yeah. So many things can happen in that space. And you might think, oh, well, it's too perfect and idealized. Why bother? Well, it's the hardest case to understand because so many things can happen. And it's a basis for understanding when we have heterogeneity, when we have all kinds of variability. You break all those symmetries and you introduce asymmetries so that you can then pick off or try to understand what's going on among fewer possible options. So things actually get simpler. And so So it's through this geometric abstract framework that we can understand some ground truths of what a model should look like that adheres to those ground truths. So things like it should be pretty easy through just some changes on, say, network edges to go from a solution that corresponds to consensus to one that corresponds to dissensus. Think about like a school of fish that comes against an obstacle and maybe they all go one way or maybe they split. It should be very easy to switch between those kinds of solutions. It shouldn't be a big deal. And so this is one of the ground truths. And so this model, if you take it to the case where everything's indistinguishable, it should give you back those ground truths. And then it allows you to then explore the more complex settings using a model. And so this is the model that I've just described to you that we've developed to explore these ideas.
And this is amazing. And just a couple of comments related to the model itself. So first of all, it seems to have to be a nonlinear model. So nonlinearity seems to be essential in modeling in this type of behaviors. And the second comment that I have is related to the parameters that you were referring to. Mm-hmm. Those parameters are, as you said, influenced not only by, let's say, the agent itself, but also through feedback from the network. So both of, let's say, the internal parameters of an agent plus the network itself affect how decision-making happens in the wild, basically.
Exactly. So we actually write down a feedback dynamic for your attention that closes the loop with opinions. So if opinions are growing in magnitude, attention is growing, and the parameters inside of this actually play critical roles. And so this idea of tunable sensitivity is to understand the role of parameters as dials that can essentially moderate or modify implicit thresholds for when a system should reject an input as an unimportant fluctuation versus have it pass through and allow the system to respond and see cascades of opinion formation. So that's the big story, because we want these systems, like I said, to be fast and we want them to be flexible. And we necessarily need the system to be nonlinear, because fast means not just exponential convergence to a decision, but also an exponential divergence from indecision. We want the system to be able to break a deadlock, break a neutral position just as fast as it becomes costly to be undecided. And flexible means that we want to be able to have this ability to adjust parameters that determine under what conditions or what parameter regimes will get this kind of ultra sensitivity that you get near this singularity, this point at which your linearization has the zero eigenvalue, and you're going to get this bifurcation to a bistable system and or tristable system. But we also want to know how to modify those parameters so that we can get into regimes where we're going to be really robust, and we don't, where we're going to be solidly either neutral or decided in the ways that we should be, and not switch and not jitter around these kinds of things. And so that's the story that we tell. The idea is to derive it very systematically so that we can really leverage the sort of a principled approach, both if we want to go back and query evolved systems, but also if we want to design systems. So we understand where we have sort of traction. Where can we design systems? Should it be in adjusting edge weights in a network, or should it be in adjusting your basal level of attention? I can say more recently we're closing the loop with an opinion dynamics model and physical control of dynamics of systems. For example, some of these tough problems where we use game theoretic approaches and optimization for trajectory planning when we're trying to, say, get automated cars to coordinate in going through intersections or lane merging or passing. These are really tough problems, and they become really tough if you don't have a way to break deadlock, if you don't have a way to kind of parse all the things that you can do, and if you have them guided by opinions, and then not only be guided by opinions, but take all the machinery that you've developed, like value functions and things that you've computed along the way for designing your control, and use those to tune those parameters. So if you can observe that something that you're doing is just not the right thing, or that one of the strategies is not the right thing, that should then become an input or a modification of a parameter in the opinion dynamics. And so this beautiful story that's now emerging about how we don't just do opinion dynamics in the abstract, we connect it to the actual physical system, and one drives the other, and then the physical system tunes and adjusts the parameters.
Automatic tuning of opinion dynamics. This is fantastic. Also, I want to mention that related also to this line of research that you've been pursuing, there are also, as usual for you, experiments in the wild that are very fascinating. This time, no animals involved, but political parties, or you looked at political polarization through these models. So I was wondering whether you can explain what was it that you found.
Yeah, that was a really exciting project with two political scientists, Kina Lipsitz and Yif Lelkes, and we were exploring a couple of hypotheses in the literature, the political science literature, that were being used to explain the asymmetry in the political polarization in the U.S. Congress. Mm-hmm. And so the idea was to use our modeling framework as essentially kind of a test bed, not so much about simulations, but really to try to understand the insights that our model could give us qualitatively about what could explain this kind of asymmetry. Mm-hmm. And so the idea was to be very even about it, in the sense of we didn't want to have to choose parameters. We didn't want to build in any asymmetry in the model itself. We wanted it to come from the data. So we were using as input actually to essentially do what we just said, to tune parameters, a measure of what's called policy mood. So people have been collecting this data from, I think it was 1959 to 2019. That's the period that we studied. It's essentially, it's crude, but it's this gross measure of the swings ideologically left and right of the voting population in the U.S. And what I don't think people had looked at before, but the question we asked was the asymmetry and polarization related to the asymmetries in those swings, both in frequency and amplitude, as they moved left and right, and how were they related to things that were happening in the different people getting elected to office or different people taking on leadership roles in Congress. And we essentially, if you could think about these parameters being tuned, each hypothesis was connected to a different parameter. So one of the hypotheses was that sort of the dominating force is kind of like a within-party self-reinforcement. And we have a term in our model that's a gain on how you feed back in a positive feedback way your own opinion. And so you can think about within-party individuals creating influence on other individuals within their party to become more and more ideologically extreme. And the other hypothesis, dominating hypothesis, what we were trying to understand if it was the dominant effect, it's called reflexive partisanship. And that's if the other party is becoming more ideologically extreme, then my party will too, like back and forth. And the third, actually, the null hypothesis, that was there was no feedback, no positive feedback, that it's just coming in through an additive input, kind of like a linear effect. And what we were able to show actually was that it was the self-reinforcement that was the only one of the three that could explain this. The reflexive partisanship was too symmetrizing. But what was really important was the nonlinear effect, the fact that you were getting close to this really ultra-sensitive point. And in fact, in our setting, it seemed like the Republican Party, which was the more polarized, was past the point, which is tricky, because the concern is that because of hysteresis, which is fundamental to these bifurcations, that it could take a while or take a lot of work to bring you back to something that's less polarized.
You're anticipating my next question. So is there something that we can do to improve our political systems or make them, I guess, in this sense, less robust or we want them not to polarize, I imagine?
Yeah. That's a good question and a big, important question. And I know, we've started conversations with my colleagues on how to use the model to explore at least some of the hypotheses that are in the literature, by even first going back and modifying a few things, like what if this person wasn't there? What if this hadn't happened? And seeing what can happen. And then seeing if we can go forward and try to understand if some of these suggestions, or maybe the new suggestions will come out of it. I mean, that would be nice if we could at least understand mechanistically in principle, how one could kind of pull back.
Super interesting. I'm sure that we could extrapolate also many other design principles from bees in terms of how to organize our societies, but this is for another episode, I guess. I guess we're gradually shifting towards the end of the episode, and I really want to talk about dancing. What does dancing have to do with control theory and all the elements or concepts that we talked about during this chat? You've done several projects that are beautifully explained also on your website. So maybe we can talk about each of them if you want.
Sure.
Just to understand how did you manage to connect these two seemingly very far apart worlds?
Yes. Well, I met Susan Marshall, who is a choreographer in New York, and she's also she's a professor and director of the dance program at Princeton. She had just arrived at Princeton and I gave a public lecture at the university that had the word collective motion in it. I think it was in nature and design. And she said, to herself, I guess, she said, I do that. So she showed up, and then she actually reached out to me afterwards, not knowing that I was
amazing,
like a crazy dance fanatic. And we talked, and she said, might we try this on dancers? And so we explored this idea of using essentially the feedback rules or the feedback laws or the models that we use to at least to model flocking behavior or schooling behavior with dancers who have been, as I said, trained to be remarkably aware of what's going on. So we could come up with these very simple rules. We ended up calling the project Flock Logic, and we ended up working first with her dancers and then teaching a class at Princeton. They have something called an atelier, and so we could explore these ideas with about a dozen students, and
nice.
And it culminated in what we called a performance event. Less of a dance, because it's something called a structured improvisation. So you're giving rules to each of the dancers, and so you don't exactly know what's going to emerge. And so this was very simple kinds of rules that we explored during this process of working with her dancers and then working with the class. For example, we called the basic rules of flocking, that every mover should stay arm's length from two other people and not let anybody else get closer than arm's length. So we actually studied this through videoing the movers and understanding how the network changes, because you can kind of back out who are your two closest neighbors or anybody's two closest neighbors and study. We actually learned all kinds of really interesting things, even in conversation with the dancers, because we had everybody inside and then observing outside. And we had all kinds of rules we played around with. Can you, without knowing who's doing it, can somebody split the group, or can somebody get the group to go out the door, navigate the room? And all kinds of really interesting things emerged from that. And then we did a couple of these events on campus in different locations, and sometimes invited people from the audience to participate and explore the role of experience with it. But it's fundamentally looking at a networked feedback dynamic system. And for me, it was really exciting, having worked with animal groups with my colleagues who are running experiments. Very hard they're incredibly creative and brilliant about asking questions, but you can't really talk to them and you can't instruct them. You can train them. On the flip side, we can design our robots to do things, or we can design simulations, but it's a little manufactured, especially in a simulation. You're putting in uncertainty. You don't have the natural bias. And so working with dancers with the human bias and the fact that they can't help themselves, they're creative and they make things beautiful. You can give them those simple rules I told you, and the dancers wouldn't just stick with two neighbors, those same two. They would move around in beautiful ways and connect in other places. And then you could talk to them about, as you change rules or play with different rules, how it felt, what constraints that were not good or constraints that give them new creative challenges. And those were the kinds of things that we explored there.
So now we're talking about Flock Logic, but there's two more projects that you then followed up on.
Yeah.
There might be others, and then Rhythm Bots.
Yeah.
I don't remember if it was because I read the reports of all these projects, and I remember they're forming basically some behaviors where somebody was becoming the leader of this flock and also somehow influencing how the whole flock was behaving just for a short period of time. I don't remember if it was in Flock Logic or there might be others. Might be wrong.
I would say both. So you'll see we wrote a paper about the Flock Logic work, and it includes an experiment where we watched them overhead and we computed for the changing network on average what every dancer, so every node in the network, what their node centrality was. And we saw that there were 2 out of, I think there were 13 dancers at that point, or 13 students. There were like 2 that were 2 standard deviations above the mean. And what was interesting was one was in front, but one was kind of in the middle towards the back. And so it was really interesting because we would try to understand where you should be or how you should move so that you could influence the group. But it also happened in There Might Be Others. So There Might Be Others is a different work a few years later. So this was a collaboration. The choreographer's name is Rebecca Legier, and it was also a collaboration with Dan Truman, who's a composer. And this is based on a piece called In C, which is a minimalist piece from the middle of the last century, in which several riffs of music were written down, and musicians come together and they play them at whatever pace they want and at whatever speed they want, whatever pitch, but they try to make it sound good. And there was a kind of a loose rule about maybe only having no more than 3 going at a time, otherwise it might be cacophonous. So this was instead thinking about, well, the starting point was movement modules, but Dan ended up composing music modules. We had percussion and Mobius percussion, some 2 percussion ensembles doing the music, and we had a group of dancers. So essentially there were something like 40 modules. So they're either like expressions of motion or there were actual steps. So there were these modules and they each had rules associated with doing them. And the dancers were told they had freedom to pick what order they wanted to go in, and as best they could make their way through as many of these modules as they could within an hour. And likewise, the musicians had the same kind of rules. But the idea was for us, so we came in with the goal of kind of this in the previous project. So how can we experiment with composition? What can we add? Thinking about the way we understand
Amazing.
Groups moving together or deciding together. And so that was really exciting. And actually, we used the terminology explore versus exploit as it became kind of the words that the choreographer and the composer and the dancers would use, you're exploring or you're exploiting. And we ended up really focusing in on trying to understand what kind of dials would introduce constraints that would give the dancers the most creative freedom. So this is, again, a structured improvisation. They're making these decisions on the fly. They want to make it beautiful or provocative or interesting somehow. And so what we landed on was this rule about how many of these modules could be sort of juxtaposed at the same time. Yeah. So they're trying to develop them and they're trying to juxtapose, make really interesting and beautiful things happen. And uncertainty plays a huge role. They're never supposed to do the same thing again. So every performance, every rehearsal is different. First, we said, what if we just say strictly no more than 3 at a time, right? They're also trying to be equitable about who gets to introduce the new one, right? So you're doing 3, and if the rule is 3 or 4, there could be still 3 going on, and someone could introduce a new one, and then once one dies out, people move to a different one. You don't pick it up again. But if you make it strict with 3, then everybody has to coalesce into 2 in order for someone to join a new one. So suddenly the people who love to luxuriate, and they suddenly have control kind of goes over to them. Yeah. And what we actually did, we tightened it to 2. Mm-hmm. We made it so that only 2 could be going on. So you had to get everybody to agree on pick one of those 2 in order for anybody to introduce a new one, which was a kind of, at first they were kind of like, but what we saw was really cool, delightful or fun, creative ways to deal with this constraint. I mean, we ended up lifting the rule for the actual performance, but it gave them along the way these kind of creative ideas about new ways to play with these rules and new things to do. So like the previous project, we developed a model. We started to think about this as in terms of an evolutionary dynamic model. We thought about this as strategies, these different modules as strategies, right? And so would you have a fraction of the population doing one versus the other? Would one then win out and the other one die out so that you could get... So we started to play with dials within this, like fitness functions and things like that, to understand how you could modulate the momentum of the piece. That's another, like, you don't want like switch, 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 but you want maybe for a while to spend time. And so
harmony, basically.
yeah.
Amazing.
So it was really amazing, right? We could have this offline too, then we could come to a rehearsal and say, let's try a few things. And the dancers are fantastic. They don't just do well beyond what you expect. They'd love to give you feedback and talk about how it felt. Yes, I felt like this was a useful challenge, because if you give people too few rules, this kind of anything's possible. It's much more interesting if there are constraints.
Yeah.
So the creative choices come from constraints, but it's picking the ones that are really interesting. So that's what we did in that piece, and it premiered in New York City in a theater in, I guess that was March 2016. That was really exciting.
And the very idea of putting some theory on top of improv is an incredible connection, very fascinating. And this idea of seeing explore versus exploit paradigm in action in dancing is something that I would have never thought about.
Yeah, we have a paper that we wrote on this, I think has the words artistic exploit tension in the title.
Yes. Of course, there will be a link in the description also to that paper. In closing, I really want to mention the last project that you focused on, so Rhythm Bots. For me, it was, I invite all of our audience to look at the videos that you have on your websites to understand how they feel about watching those videos. Because for me, at least personally, I really felt in peace almost. It was a meditative experience, even not being in the room of where this installation is. So we're talking about an installation that consists of basically slender robots that synchronize rhythmically with who is in the room. They have sensors, so they can measure what's going on. And based on that, they make decisions about how to oscillate. This is the way I would describe the project, but maybe you can tell us more.
Yes. So this is a project to explore rhythmic entrainment and synchrony in the presence of a human audience with mechanical movers. So rhythmic entrainment refers to the effect, the emotional effect that rhythm has on us, particularly in sound. It's been very well studied in music. Our brain waves are probably synchronizing with the frequencies that we're hearing, and it can make us feel really good and relaxed. And I had been part of a study that my colleague in dance, Susan Marshall, had run, and she's created a piece called Rhythm Bath with dancers that move in these very soothing rhythmic patterns. And the idea really was to try to understand how people can feel grounded. And it's kind of this idea of a performance installation piece. And I started to wonder, did it have to be a human mover? So we're already wondering about visual cues and movement and how that makes us feel as opposed to the sound. And we were experiencing it really making us feel good when we were watching dancers. But the question was, could I do this, or could we do this with something mechanical? Mm-hmm. And so we created these bots. We call them rhythm bots, and each one is a slender, like a pendulum that's kind of, the fulcrum is low. And what we've done is we created a system of linear actuators connected to the bottom of the pendulum through springs. Mm-hmm. So we have this muscle-like feel. You can even think of these as like little neurons that are oscillating. But so we have 3 linear actuators that are uniformly distributed around the circle. So if we oscillate them as sinusoids, 120 degrees out of phase, we get a circle. But if we make, we get all kinds of patterns and all kinds of rhythms. And the little circle below turns into a bigger circle above because the fulcrum is low. And then we have them synchronized. So each one has its own little Raspberry Pi underneath, and they move together in these beautiful patterns. And we can explore what it feels like to be around them, what frequencies, what kinds of patterns work. But the other important piece is that we put cameras on them and we do video processing of the audience, so we can respond, have them, the robots respond to just the presence or the density or the flow or the distance of the audience members. So there's a little bit of a conversation in some sense, so that people feel like they're being responsive. I mean, one of the first things we did was just when somebody gets close, actually all the robots will stop and acknowledge the presence. And then they'll pause, and then they'll start up almost with like a little giggle because of the springs. You can move them, and we enjoy this little kind of wiggle giggle kind of thing, which is like a greeting. And then they do something different. So they're responding to the people, but it's evolving. And my next step is to engage with, in a collaboration with Dan Truman, who's the composer I worked with previously, and Jane Cox, who's a lighting designer. And we're going to explore the next phase of this, trying to understand the role of the sound that the stepper motors make, which is really kind of fantastic. So we're going to mic it and play with that, and also with light. So these are very simple. We're not trying to make them like themselves one note beautiful things. It's really meant to be a system that engages you visually. And so, but we want to understand what light can do in that sense, because we're trying to elicit these moments of peace. And I just have to say that it was kind of an extraordinary experience to develop this during the pandemic, to really think about how robots could make us feel good and how robots could make us feel connected. And if you watch the videos, you'll see we're wearing masks still, but it's an interesting way to think about creating connection among people, but in the presence of some mechanical system that is providing some of the glue or just making us feel calm enough to feel like we're all together.
One more comment is, again, related to all of these projects, is that now it seems to coalesce into this CreativeX that I heard about. It's a transdisciplinary group uniting people from arts, science, engineering, bringing together a wide range of experts. And what is the goal of CreativeX that you're championing lately?
Yeah, so CreativeX is a group of us at Princeton. So faculty and others in dance, theater, music, visual arts, and then civil engineering, mechanical engineering, computer science, chemical engineering, where we have been actually talking for over a decade. And it just basically in conversation with one another. Many of us collaborate, but many of us just get inspired by one another. And when we're together, we live in this space that's outside of our formal disciplinary spaces, so that we can really think. We're all creators, right? We're all making things and thinking about new ways to approach questions. And we find that we have so many questions and perspectives to share and to find parallels within. So we have consolidated ourselves in something called CreativeX. And so I'm expecting shortly we'll have an opening with our website, but we've already been doing a lot of work to document all of these projects that are going on and how they're in conversation with one another, how the arts and engineering are informing one another, how in what cases we think alike, in what cases we have tensions that we share, or tensions between the fields, and what does that mean for our creative pursuits.
Of course, there will be a link in the description when the website will be available. Since we're on the subject, and before I ask you the last question of this episode, how does one enhance creativity? What's your take on that? Because you've been immersed in this world for such a long period of time. Is there anything that we can do to incentivize that?
Well, I think just to sort of allow people to feel unconstrained and not feel like they have to follow a particular model, right? I think people can sense what gets them excited, what gets them curious. I think certainly for me, it's always been pursuing directions where I feel I can be creative. And also this idea of opening yourself up to allowing yourself sort of lifelong learning, right? I mean, I consider myself a student of biology. I mean, I feel like I'm a student of so many things. I can remember when I first arrived at Princeton and started to meet people in ecology and evolutionary biology, saying to my former advisor, Krishna Prasad, saying something like, "Oh gosh, maybe I should have studied ecology and evolutionary biology." And he looked at me and he said, "Naomi, you're a control theorist. You know about feedback. You can, you can study it from your perspective." I mean, so I think that's one of the beautiful things about our field. I think feedback is ubiquitous. You don't want to take on the whole world. I mean, some people say, "Oh, you're working on these different subjects," but they're all, for me, very, very tightly connected. And one leads to new directions, but it's not like you don't want to spread yourself too thin. But I think this idea of just sort of allowing yourself to not feel constrained, right? picking any of the sort of areas that intersect with systems and control theory really open doors, right, to creativity.
So it's a sense of freedom that could be
a sense
the
of freedom.
enabler.
Yeah, and I think sometimes like CreativeX, getting outside of the community. I mean, look at, so many people in our field have many other kind of avenues, even venues where they publish, where they go to conferences, and that's because this is what built their creativity, right?
This is amazing, and also leads me, it's a fantastic springboard towards the final question of this episode, which I tend to ask to every guest that comes on the show. And this is advice to future students, so people who are approaching the field and that are seeking for inspiration. What would you say to them?
I think our field is really, it's so wide open, right? Because of, as I said, because of the ubiquity of feedback. I mean, it's sort of everywhere in the natural world, and it's kind of necessary everywhere in the design world. So all of these principles, the way we understand robustness, the way we understand flexibility, the way we understand resilience, we have so much to offer. And I think, not being afraid to dive into a new direction of mathematics or a new application area. I mean, not everything leads to something exciting, and so you have to be careful, and you don't want to spread yourself too thin. But I think there's so much opportunity. I would just be humble about it, be modest about what we can say. It's super exciting to work on applications in the field, even if you're not the expert on making that happen, or cross-disciplinary, like in biology or neuroscience, even if you don't have the training. Knowing that going into it, you're not exactly sure what our tools can do, but really listening, really engaging with the people who are the experts. And if you become fascinated with their questions, then it can be a good thing. You want to find ways to use this theory that make you want to understand and answer the questions that your colleagues want to answer.
Well, Naomi, it's been a wonderful journey. It's been a real pleasure to have you on the show. Thank you so much for joining us.
Thank you so much for having me. It's been a lot of fun.
Thank you for listening. I hope you liked the show today. If you enjoyed the podcast, please consider giving us 5 stars on Apple Podcasts, follow us on Spotify, support on Patreon or PayPal, and connect with us on social media platforms. See you next time.